Mhm. Okay, hello everyone in a new video. Then we have reached part 4 of chapter 13, which is the chapter of rectilinear motion for grade 10 students. Now we are going to complete the explanation in this chapter, and we have reached section number 6, which is the motion of a puck. So what is a puck? In this case we are considering the puck to be an object. So the puck is an object moving along a support in which it registers a dot, and here the dot, it means point made up of ink. So the puck is an object moving along a support in which it registers a dot for every for a certain, let me say, for every time interval tau. Okay, so let me say that this is the x-axis, okay, and this is the origin. So the puck starts from here, and these dots, let me say, without mentioning the origin, so let me say these are the registrations of the puck. So this is the point A0, this is the point A1, this is the point A2, this is the point A3, and this is the point A4, etc., so on and so forth. So the puck is moving along this axis. So the shape of the puck will be something like this. It is moving along the x-axis, and for each time interval tau, so tau may be, for example, 0.1 seconds, 0.2 seconds, etc. So at the time, tau is an interval of time. For each interval of time, this puck is registering a dot. So in such type of problems or applications, we need to study the type of motion of the puck. So in this case, we have no equation. So previously, we used to study the motion of an object whenever we have the time equation. For example, if x is given by 2t squared plus 4t, we know that in this case the type of motion is UVRM because the position is quadratic in time. But here we don't have any relation between the position and time, velocity and time, acceleration and time, so we cannot determine the type of motion. In this case, we will refer to the registrations of these dots in order to determine the type of motion. Okay, and actually we will determine the type of motion by referring to the average velocity and to the average acceleration in a sense. Now, first we need to note the following thing, is that the time interval tau, or let me say it is the time interval tau is very small. In a sense that tau can be equal to 100 milliseconds, 200 milliseconds, and milliseconds means that we need to divide by 1000, which is equal to 0.1 seconds, 0.2 seconds, or maybe tau is equal to 50 milliseconds, which is 0.05 seconds. So in this case, the time interval separating these events is very small. Okay, now we can determine the speed at the position So A0, A1, A2, and A3, A4 are the positions of the puck at this point, this point, this point, etc. So we can say that V1 is the speed of the puck at the point A1. Now we can determine the speed at the point A1. Now, in order to determine the instantaneous speed V1, we need to determine the type of motion. We don't, in this case, we don't know the type of motion. However, in this special case, V1 can be determined using the formula of the average speed, which is equal given by d divided by delta t. So here I'm using the formula of the average speed to determine the instantaneous speed, simply because the time interval delta t is very small. So whenever the duration delta t separating two events is very small, instead of using the formula of the instantaneous speed, we can use the formula of the average speed. So in this case, what does V1 represent? It's the speed of the puck at the point A1. And in this case, in order to calculate V1, so how do we calculate V1? Since we are calculating the speed at this point, so the speed at this point will be the distance around this point, which is A0, A1. So it would be the distance A0, A1, sorry, A2. So what does A0, A2 represent? It's the distance along the point, this point, that we wish to calculate the value of the speed. And in this case, what's the duration? So as we have mentioned previously, so from this point to this point, we have the duration tau, which is the time needed for the puck to register at any dot. And from here to here, it is separated by another time interval, which is given by tau. So the duration delta t is 2 tau. Okay. So for example, if you are interested in determining the speed V2, so V2 represents the instantaneous speed of the puck at this point, which is given by d divided by delta t. We are using the formula of the average speed. We are allowed to because the duration delta t is very small. So what's the smallest distance around the point A2 is given by A1, A2 plus A2, A3, which is given by A1, A3 divided by 2 tau. Now suppose if this is another, okay, this is A4, what about V3? V3 in this case would be the distance around A3, which is given by A2, A3, A3, A4. Now in this case, we will be able to calculate the values of V1, V2, and V3. If V is constant, then the type of motion is set to be URM. If this distance is increasing, then the type of motion would be UVRM. Not only increasing, but decreasing, as we shall see in the exercises. And here notice that because this distance is changing, we expect that the type of motion is UVRM. Okay. Now moreover, also if you want to determine the acceleration, so suppose in this case you are interested in determining the acceleration A2. So A2 simply would be given by delta V by delta T. We are using the formula of the average acceleration to determine the instantaneous acceleration simply because delta t is very small. Okay. So in this case, how do we calculate the acceleration A2? So it is the variation in speed over the variation of time. So simply it would be given by v3 minus v1 over how many time intervals? 2 tau, okay, as we shall see in the exercises. So this is it for section number 6. Now we are interested in some vectorial quantities, so let me move to section number 7. Velocity and acceleration, and this is given by vector quantities. Then let me start by the velocity vector. Now suppose here we have a solid S, an object S, and the direction of motion, this is the direction of motion. So this solid S is moving from left to right. Now we know that every vector have 4 properties and they are given by the builder. So in this case, so here whenever we say the velocity, because we didn't distinguish between average velocity or instantaneous velocity, for sure we are talking about the instantaneous velocity. So we have the point of application, the line of action, the direction, and the magnitude. Now the point of application would be the center of mass or center of gravity of the moving object, in this case of S. Now the line of action would be along the direction of motion. So in this case the direction of motion is horizontal. So the line of the direction, so the line of action of the velocity vector v would be also horizontal. Now the direction is with the direction of motion. And the magnitude would be the speed. And we know how to calculate the speed by studying the type of motion or the dots of the moving puck. Now as for the acceleration vector, so the point of application would be also the same. The center of gravity of S. Now the line of action would be along the direction of motion. Now here by the speed I mean the value v. Okay. For this reason we used to say that the speed is equal to v on net S, because whenever we have a vector, if we were interested in the magnitude, we drop down the vector. So along the direction of motion. Now as for the direction, let me say first the magnitude is the acceleration A, And let me say that the direction depends on the value, on the sign of A, as we shall see in the exercises. Okay, so this is it for the explanation of this chapter. Now let's move on to the following exercises. Now this will be clarified during the exercises. And we have reached exercise number 6. So we have that a puck B is launched on a horizontal table. Just 1 second. A puck P is launched on a horizontal air table with an initial speed V0. The figure below shows the registration of the puck during constant time interval tau is equal to 100 milliseconds. So tau is equal to 100 milliseconds. Knowing that millisecond is not the SI unit of time, in order to convert from milliseconds to seconds, we divide by 1000. Then 100 divided by 1000, this is equal to 0.1 seconds. And this distance is given by 4 centimeters. Now, for sure we are interested in studying the type of motion of the puck. Okay, so I will do it only just for one exercise. As for the rest, it will be the same. So whenever you are interested in studying the type of motion, we need to write the URM and the UVRM equations. As for the URM, they are given by x is equal to vt plus x0. V is equal to a constant and the acceleration is 0. Whereas for the UVRM, they are given by x is equal to half at squared plus v0t plus x0. V is equal to at plus v0. Here we have that d is equal to vt. We have that a is equal to a constant. V square final minus v square initial is equal to 2ad. And we have that d is equal to at plus v0. So we have at squared plus v0t. Among all of these equations, in the case of the registration of the puck, we are only interested in this one and in this one. So whenever the acceleration is 0, the type of motion is URM, and whenever the acceleration is constant, it means it's a varied motion. Now, if we're okay, let's start. Number 1, they are telling us indicate with the justification the trajectory described by the motion of the puck. So notice that the motion of the puck can be studied by referring to these dots. All of these dots belong to the same straight line. So let's say since the registered dots belong to the same straight line, then the trajectory is rectilinear. Now in number 2, they are asking us to calculate the average speed between m0 and m7. So V average is given by d over delta t. And here they are asking us between the points m0 and m7. So the distance from m0 to m7. Okay, so here it seems that all the distances are the same, separating the dots. So all of these are 4 centimeters. So how many do we have? 1, 2, 3, 4, 5, 6, 7. So 7 times 4. And in order to convert from centimeters to meters, we need to divide by 100. Or times 10 to the power minus 2. And how many time intervals do we have? From here to here it's 1, so if we count them it will be 7. Then 7 times 0.1. Now plugging this on the calculator, then the value of the average speed will be given by 0.4 meter per second. So the average speed would be given by 0.4 meters per second. Now in number 3 they are telling us to calculate the instantaneous speed V1, V3 and V5 at M1, M3 and M5 respectively. So let's start by the speed V1. Speed V1 at M1. So these are not part of the answer, they are on the scratch. So the speed V1 at M1. So here we don't know the type of motion, whether to use this formula or this formula. We didn't specify whether it's URM or UVRM. So, but we can use the formula of the average speed because the time interval delta t is very small. So we can say that it is given by d over delta t, but here we are calculating the speed at point 1. So we take the distance between, so the closest distance around the point M1, which is M0, M2, over how many time intervals, which is given by 2 tau. So this is equal to 2 times, so 4 plus 4, it would be given by 8 times 10 to the power minus 2 divided by 2 times 0.1. So now if we plug this expression on the calculator, so here no need for the 2, okay? So it's simply given by 8 times 10 to the power minus 2. Now plugging this on the calculator, then the value of the speed V1 at the point M1 is given by 0.4 meters per second. Now as for the speed V3 at M3, so V3 in this case is given by d divided by delta t. So what does d represent in this case? Because we are calculating the instantaneous speed and this is the average speed, we are allowed to use this formula because delta t is very small. So d is the smallest distance around the point M3, which corresponds to 8, which is 4 plus 4, which is this distance M2, M4, divided by 2 tau, which is equal to 8 times 10 to the power minus 2 divided by 2 times 0.1, which is also equal to 0.4 meters per second. Now as for the speed, the speed V5 at the point M5, so it's given by V5 is equal to d divided by delta t, and now we can you can now notice the pattern. So it'll be given by M4 M6 over 2 tau, so a point before and a point after over 2 tau. So M4 M6 over 2 tau, which represents the distance around the point 5 M4 M6 over 2 tau, which is equal to 8 times 10 to the power minus 2 over 2 times 0.1. So this is also 4 and this is also 4. Now plugging this on the calculator, the value would be given by 0.4 meters per second. So what is the conclusion in this case? V1 is equal to V3 is equal to V5 is equal to 0.4 meters per second. So the speed is constant, which means the type of motion is URM. Now unfortunately we have written down these equations and we haven't used them. Now probably we'll use them in part 6. Now in number 4 we need to represent the velocity vector V1 at M1 using a convenient scale. So we need to represent the velocity vector V1 So let's recall what are the properties of the velocity vector V1. Let me say that first we start by the point of application. So why I'm listing the properties although they ask me to represent? Because the properties help us to represent properly. So the line of action, the direction, and the magnitude So if we recall back to the following section, we can notice that these are the properties, the center of gravity of S along the direction of motion, with the direction of motion and the magnitude would be equal to the speed, which is v. So let me write down the center of gravity. So in this case, the solid is named to be P and not S. We will use the same notation. So this is P. Now the line of action along the direction of motion. So what is it? The direction of motion. So now notice the direction of motion in this case, this is it, which is set to be the horizontal. So this is the center of gravity P, the horizontal, here of P. Now what about the direction? If we recall to the previous page, the direction is with the direction of motion. And here the direction of motion is from left to right. So it is moving from left to right because it started with the initial speed at this point, that's moving from left to right. So the direction is to the right. And the magnitude would be the speed, which is the magnitude of this velocity vector. We drop down the vector, it's given by v1. And we have predetermined the value of v1 and it's given by 0.4 meter per second. So all of these properties we have listed them down in order to represent the vector properly, because they are telling us to represent the vector at m1 using a convenient scale. Notice that the scale is not given, we must choose the scale. Now what is a scale? The scale is a connection between the magnitude of the vector that we want to represent and a unit of length, which is 1 centimeter. So 1 centimeters must be connected to a number here, which is expressed in meters per second, in such a way when we put this value inside the scale, we will be able to find the length of this vector. Now previously in grade 9, the convenient scale is already given in the exercise, but in this case we need to extract the convenient scale. So in order to the easiest way to extract this scale is simply divide this by 2. Okay, so 0.4 divided by 0 by 2, it would be given by 0.2. So this is the scale that we are interested in. Okay, so I repeat, how do we extract the scale? After we have listed the properties, here we know the magnitude. The scale is the connection between 1 centimeters and the magnitude, so we place here 1 centimeters and simply we divide the magnitude by 2, so this is the scale. Now we need to determine the length of the vector v1 that we are interested in representing. Recall that I have listed these properties because it will be easier for us to represent the vector. Now if this is the chosen scale, what would be the length of a magnitude of 0.4? So 0.4 meter per second corresponds to what? So in this case we cross multiplied, and 0.4 multiplied by 1 divided by 0.2, this would give us 2 centimeters. So now you can notice that we have chosen the scale in such a way that the length of the vector would be 2 centimeters, which is the easiest length that we can draw on a piece of paper. So what is the center of gravity of P? In this case it is given by m1, which corresponds to v1. So here let me say m1. So this is the answer. Now here so we place here the point m1. So we will represent the vector v1 horizontally to the right with a length of 2 centimeters. So this is the vector v1 of length 2 centimeter corresponding to 0.4 meter per second according to the scale, and we place this in order to justify that this is 1 centimeter and this is 1 centimeter. Okay, actually this is not important for us. So now we have reached number 5. They are telling us calculate the accelerations A2 and A4 at M2 and M4. So let me start by the acceleration A2. So here we don't know the type of motion yet. We didn't specify the type of motion in order to use the following equations. So the acceleration A2 can be calculated using the formula of the average acceleration, which is given by delta V by delta T. Although here this is the instantaneous acceleration because it is at a specified instant, but we are using the formula of the average acceleration because delta T is very small. So what does delta V represent? It's the speed before minus the speed after, which is V3 minus V1 divided by 2 tau. Now V3 we have predetermined, which is given by 0.4. So here we have determined V3 and it's given by 0.4 meter per second minus 0.4 over 2 tau, which is given by 2 times 0.1. Now here this is equal to, so 0.4 minus 0 is 0 divided by 0.2, which is equal to 0 because 0 divided by any number is 0. And no need to put a unit for 0 because 0 multiplied by anything is 0. So A2 in this case is equal to 0. And this verifies the fact that indeed the type of motion is URM. Now let's calculate the acceleration A4. So acceleration A4. So here we are talking about the instantaneous acceleration because it is at specified instant, but we don't know the type of motion, so we cannot use any of these equations. However, because the time interval is very small, we can refer to the formula, which is the average acceleration delta V by delta T, which is equal to V5 minus V3 divided by 2 tau. So it's the final speed around the point 4 minus the initial speed around the point 4. So recall that V5 is also given by 0.4 meter per second. So this is 0.4 minus 0.4 divided by how many taus? 2 taus, which is 2 times 0.1. And this is equal to 2 divided by 0 divided by 2 times 0.1, which is equal to 0. And no need to place a unit here because anything multiplied by 0 is 0, so A4 is equal to 0. So the instantaneous acceleration at the point 4 is 0. So they are telling us deduce the nature of motion of the puck. So since the trajectory is rectilinear, and the speed is constant. Why the speed is constant? Because we have proved this in part 3. And between the brackets 0 acceleration. Then in this case, then the type of motion. So 0 acceleration means that this is 0. So the type of motion is URM. So this is it for me in this video, guys. In the next part, part 5, we'll complete solving exercises on this chapter.